Okay. Yeah, you can start, Girish.
Yeah. I'm Girish on behalf of Team Spectrodon. So in this presentation, we'll be taking you through AMD's cache way predictors and possible attacks through it. So the plan that we have is first we'll be giving you some intro about what a way predictor is. Then we'll be telling you how we can exploit it, followed by how we can stop these attacks. So way predictors, as the name suggests, it is in order to predict which way a particular virtual address is present in. The reason for this is that in case of a hit, you do not need to access all of the ways within a particular set. Rather, you will be accessing only one, which is faster, and also you have low power consumption. On the other hand, in case of a miss, you will have to forward the request to L2 cache despite it already being there within L1D cache. Most modern AMD architectures include way predictors, and the way they do this is by holding an additional structure where something called a mu tag is stored for each cache name, and this mu tag is computed using an unknown hash function of the virtual address. So we go for some more details. This data structure that is visible here, that is known as the way predictor table. Here, for each set across all ways, you have the mu tags of the cache, the address that brought that line into cache. And once you get the access for a particular virtual address, you compute the hash, obtain its mu tag, and check it across all of the ways within the particular set. Although this might seem like it has no difference compared to the checking the physical tag across all of the ways, this performance delay will be subsumed within the TLB access before the physical tag is checked. Now, in case of so like in case the mu tag is missing within all of the ways, then you don't need to go ahead with the TLB and then check the physical tag on all of them. You can directly forward the request to L2 cache. So, yeah. And similar to how within a particular cache set, you cannot have two ways which have the same physical tag. You cannot have two different valid ways within the same set sharing the same mu tag. One of them will be marked invalid. Due to this, when you have two virtual addresses which result in the same mu tag and you access them one after the other, one of them will get marked invalid and the access will have to come through L2. This timing difference is visible clearly here. So we use this timing difference to build an oracle of whether two virtual addresses result in the same tag or not. Now using this oracle, we can construct sets of virtual addresses, essentially partition the virtual address space such that within each of the set, all of them result in the same representative mu tag. The authors utilized this algorithm and generated two physics sets, which corresponds to an 8-bit hash. Now, they made an assumption that this hash function is a linear in terms of the virtual address, and in addition, bits 6 to 11, which correspond to the set index, are not utilized within this hash. Now, within a particular set, all of them have the same mu tag, which implies we get a set of linear system of equations within them. Now you solve them within each set and you obtain the hash function. They tested this against most modern AMD architectures and they found that bits 12 to 7 of the virtual address are used in them. You obtain equations corresponding to each bit, but the order of which these bits appear is still unknown. This way prediction table is shared across all threads. Essentially, it is one per physical core, but at the same time, when you have access to different virtual addresses, each from a different thread, but still having the same mu tag, no collision is observed. One is not evicted, which implies the way prediction is not purely based on mu tag. There's an additional extra part which is based on which thread has loaded this or is accessing it. That is the thread component of it. Although we mentioned that two different accesses across threads won't evict it, but there's one exceptional case, aliased physical addresses. You have two virtual addresses, V prime, both map to the same physical address. Their mu tags will not be same, usually won't be, but still, since both of them map to the same cache line, when you access the first one, the mu tag present there will be loaded. But when you access the second, even though the cache name is present within the L1D cache, due to a mismatch of the mu tag, it will forward the request as an early miss to L2. So this allows you to effectively treat as though loading V evicts V prime, and this is applicable across threads, but restricted within the same physical core. Now we consider the possible attacks that we can do based on this cache way-predictor. As we saw this picture in the process of constructing the oracle, when you access an address, the time in case somebody else has accessed a different address with the same mu tag is different. This timing difference allows us to get a side channel on the victim's access. Two different attacks were generated based on this with different threat models. The first one is collide plus probe. The goal here is to monitor the address V of the victim. You prepare a different virtual address V prime which maps to the same set and has the same mu tag. When you access that virtual address, it is brought into the cache as well as inserted into the way-predictor table with the mu tag. In case the victim does not access, both the way-predictor table state and the cache state remain intact and the access is served from the L1D cache. On the other hand, when the victim accesses, the victim's corresponding cache state is brought into cache, and even though the mu tag is same, the old mu tag entry is deleted. Now when you try to probe for V prime, a mu tag match is detected. You verify the physical tag for V3, which was corresponding to the virtual address V, and the physical tag match fails. This request must now only be served from L2. This timing difference allows us to monitor the victim's accesses. The attack collide plus probe gives us cache line level monitoring, but you do not require any shared memory. The only requirement that you will be having is high precision timer, since to distinguish between a victim's accesses, you will need to be able to distinguish between an L1 access and an L2 access, unlike in most attacks where you will be distinguishing between LLC access and LLC miss. Another major requirement of this attack is that the victim and attacker must have the same logical core, the same thread within the same physical core. We will try to remove the last requirement, sharing the same logical core. We had mentioned aliased addresses, which allow you to effectively evict victim's address from a different thread within the same physical core. Now we merge collide plus probe with this attack. The new one is called load plus reload. Here again we try to monitor the address V of the victim. We prepare V prime, which has the same physical address, and we access it. Now here it is loaded into cache and the tag corresponds to the tag of V prime. When the victim doesn't access, both states remain the same. Your access will be served from L1D. When the victim accesses, it's the same cache line, but the tag now corresponds to the tag of the victim. When you access, a mu tag mismatch is detected, and despite the cache line being present within L1D, the request is served from L2. This monitoring is across different threads. We'll now be seeing how significant these attacks are. The standard way to test it is through covert channels. There is a sender and a receiver. They determine on two different virtual addresses which have the same U tag and the same set. To send 1, the sender will access the set. To send 0, it does not access it. In addition, to avoid this timing synchronization implicit here, another solution proposed was you determine two different sets. Accessing the first set means sending 1, second set means sending 0. By using the second method, you can send up to 32 bits in parallel. Using the first one, you can send up to 64 bits, which is why we can see in the first plot, after the 64th bit, when you send more number of bits in parallel, the transmission rate becomes almost constant. Now we can see the comparison of this transmission compared to other state-of-the-art attacks. It is much higher compared to them due to being able to send 80 bits in parallel at the same time. The more number of bits you send in parallel, the higher the error rate comes, and there's a huge spike in it near around the 64th channel number. This is because of the fact that you are using the same set to send more than one bit. To mitigate this, the solution proposed was to add error codes to the transmission via a Hamming code. So here, after introducing that, the error rate remains 0 almost to the 64th cache line. Beyond that, it remains close to 1. The second attack that was performed was breaking of ASLR. The main novelty in this was their attack on Linux kernel, which was done on an AMD system. It was the first attack of its kind. So here, within the Linux K ASLR, you have 9 bits of entropy, which maps to the possible allocations for the page. When you access a global variable within a particular page. The virtual address
Girish,
offset, yes.
maybe you should explain ASLR before jumping into the attack.
Oh, yes. Like ASLR is essentially like address space randomization. In order to like most standard attacks, you will need to determine the address regarding where you jump to when you overwrite. To mitigate that, you randomize the address space beforehand during runtime. This prevents you from exploiting most of the standard attacks. So KASLR is the randomization of the kernel pages that is done during boot time. It's a one-step process, while the user process ones are done during each execution. Similarly, each web page when it's rendered, the sandbox is essentially randomized as well, which is the last class of attacks shown here, the last three. So KASLR is a specific one. So within that, when a global variable in the kernel is accessed, the virtual page offset is determined. So you can decide the least significant 21 bits of the address accessed. And in addition, since you know the U tag that was accessed, you can also determine the next 6 bits or 7 bits more to be more specific that was accessed, reducing the entropy to just 2 bits. Now the other attack that was considered was first round attack. The number of encryptions shown in a first round attack is a measure of both the false positive rate as well as the false negative rate to some other extent. You can see from these numbers that collect plus probe and load plus reload. Yes,
again, the same comment. What is the first round attack?
Like within an AES encryption, during the first round, in order to, you will be having 3 steps: substitution bytes, row shift, and column mixing. Within these, you will combine these 3 steps into a single step using something called AEST tables, which will be predetermined
Okay,
values.
I don't think you need to explain that. You may say that, AES itself can be attacked maybe the initial rounds or the final round or the intermediate, right? But here
It's
you are
first
focusing
round.
on the first round, right?
Like the first round attack will allow you to retrieve the high order nibble of each byte in the key, based on which cache line exactly was accessed. So the number of encryptions you'll need to determine this depends on the number of false positives you obtain. So collect plus probe and load plus reload both have much lower number of encryptions required due to a lower false positive rate compared to prime plus probe. After all these attacks, they proposed 4 different mitigations against them, 3 of which are hardware mitigations. Fourth one is a purely software mitigation. The first one is dynamic wave prediction. Here, every miss of the wave predictor might result in you going to L2 cache to fetch data, even though it might be there within L1D already. So the proposed solution was you disable the wave predictor when a high number of misses is observed, enable it when a low number of misses is present. This both improves performance and mitigates this attack. Second, a keyed hash function. The hash function done currently is independent of which process is using it. The proposed solution was there's a process dependent secret which is embedded into the hash. This prevents using the hash function that was determined by the attacker on the victim. Third, state flushing. For the KASLR attack, you need to know what was the UTAG of the address that the kernel had accessed after the context switch from the kernel to the attacker. One solution was to just flush the wave predictor on all context switches. The fourth was a purely software mitigation. So here, since the total number of mutags that you can obtain is just 256, you can clone all the data that you intend to keep secret into 256 different copies, each of which map to a different mutag. So when the attacker monitors the utags, he cannot determine whether the secret is accessed or not. Thank you. Next, we can take questions.
So what's the size of this wave predictor structure?
It was for 1 per way within each set. The most recently used one. Just the current usage was there. Equivalent to the physical tag for each cache time.
Okay, and then is there any comment if they don't use wave predictor? What's the performance degradation?
And they hadn't implemented the first 3 mitigations because they were hardware based ones. They linked to another different paper wherein they had used dynamic wave predictor for performance reasons.
That's okay. My question is pretty simple. So if wave predictor is providing me, let's say, some negligible performance, But I think if it provides negligible performance, they should not have put it on the processor in the first place.
Yeah, one reason was performance, the other was also power consumption reduction.
Yeah, the
you
energy.
need to just load one way at a time.
Okay. So this can be clubbed again with speculative, right? So
Yeah,
if
they had used this to show a Spectre attack on AMD processors.
okay. Mm-hmm.
The KSLR break was significant for that. Since to first determine where was the Spectre gadget, you need to first break KSLR to determine exactly where you should attack.
Your presentation was overall good. Just the last slide was a bit text heavy. Otherwise, it was good. Okay. Other questions?
Hi. So, do they show like AES key is compromised in this? Like how many bits of AES key is compromised, or only the first round is?
Yeah, only the first round attack is done, which will compromise the high order nibble. Essentially, most significant 4 bits of each byte of the key. So
Okay.
just a second. Like here they have shown the accuracy of this attack. The number of times the correct high order nibble was detected. So if all the diagonals are blue, it means you have detected the correct high order nibble. Only the most significant byte is sorry. Only the most significant 4 bits are varied here.
Okay, so only 4 most significant
bits per byte of the key. To retrieve the full key, you need to integrate the first round attack with second round or other attacks.
Yeah, because there can be 16 or many rounds of, right? Okay.
There are generally 10, 12 rounds, 10, 12 or 2.
Hi, I have a question.
Yeah.
So, what's the cache hierarchy they have considered in the paper? I mean, whether it's inclusive or exclusive or not 9. I mean, not neither inclusive.
There's no assumptions made on the cache hierarchies type. It fully operates within the L1 and the Way-predictor.
Okay, why I'm saying this, because when you said if there is no hit at L1, so in that case it will go to the next level cache, right?
Yeah.
So it might be that the block which was already there in the L1 cache, it's not in other levels of the cache, and then data has to come from the DRAM. So there is a higher penalty which will be given, which needs to be paid in case of data which was present and is not found there, right? So that is why I asked about cache hierarchy. One more question I wanted to ask is that
No, but Yasika, if something is not present in L1, then we won't be able to comment whether it will be a hit at L2, L3 or wherever, right? Irrespective of the hierarchy.
yeah,
There
no,
one issue, like it was present within L1, but the Way-predictor marked that cache line as invalid due to a mutac collision. So when you access it, you can make some assumptions based on the inclusiveness or exclusiveness of the cache hierarchy.
yes,
But generally, the paper didn't mention anything, but generally AMD has always been
using non-inclusive caches.
creating non-inclusive or exclusive caches. So they are not proponents of inclusive caches.
Okay. Yeah. My point was, so there are chances that the data
Will
which was
come from
there,
a lower level.
yeah, it might will have to come from DRAM also.
Yeah.
Yeah. One more question I have is, because it is operating at virtual addresses, so so the kind of performance benefits they are getting is because of the TLB, like the data, I mean the physical address which was supposed to be come from TLB. So that time is saved, that latency is saved, right? Other than that, what else is there which they are trying to save by way prediction?
That time is not exactly saved. In case of a miss, you would directly go to L2. So there, that time may be saved. But if it was a muTag hit, you will still need to wait for the TLB output to check the physical tag of that one way. The main benefits is in terms of power consumption.
Okay,
You
so
don't
power.
need to activate all of the ways, but only one of them.
Okay, so now, okay. So, I thought that there might be some latency of the mux also, which eventually gives one output among
Yeah, that
many.
mux will still need to be there to check across all of the mutags for that particular set. But it will
Oh,
be of lower size because you don't need the full physical tag size, but only 8-bit hash.
okay. I could not understand mute concept, but okay, but I
It's
got your
a
point.
8-bit hash of the virtual address, a particular
Mhm.
section of the virtual address.
Yeah,
So
yeah.
as you can see in the slides, I think Girish can show that picture. We had an equation, right?
Just a second. So this is the mutag. The output of this on virtual address V is this is the mutag.
And then they have to have this table also, which is an extra overhead.
Yeah, it's an extra overhead on top.
Okay. Um, okay. Okay, I haven't completely, I haven't got the complete picture, but I understood that they are more oriented towards the energy benefits, they are saving energy
Yeah,
than that of the latency. Yeah, I was assuming that it's more for the performance benefits.
performance
Okay,
benefits might be more of a side result rather than the main goal of this.
okay. Thank you.
Yeah, I have another question. So, is there a possibility of cache coherence attack with way predictors? If let's say two cores that they are sharing, or let's say two processes, not cores. Yeah, even two cores. Why processes? Two cores that they are, let's say, sharing a library. So in this attack, there was no requirement of shared memory, right?
There's no requirement of shared memory, but
Yeah.
both attacker and victim should be in the same core.
Yeah. So that's a hyper threading concept, right? At least multiple threads should be active at a given core. That's okay. What I am suggesting is, what if you have addresses that are actually shared across multiple cores? Okay, that's why cache coherence comes in. And then I can't figure it out how exactly you can do it, but you can create a timing channel based on the way predictor, colliding accesses, and the other subtle points that you mentioned. It's like, let's say I want to read the address, and that address is present in someone else's core also, right? And it's highly likely that even way predictor will have a mutag, right? So can I generate a sequence of events which can actually, finally give me a timing channel, or some kind of channel which can be exploited along with the coherence protocol? That was my question. Is the question clear, or I'm fuzzy?
Yeah, like we need to get a side channel on a different core by
Yeah.
using the way predictor state on this core.
Yes, exactly. Mhm. What about because the coherence states will be affected even in the way predictor, right? That's my understanding. No?
I'm not sure regarding that. Like
Okay.
the AMD documentation does not have that much detail on the
Obviously.
The only information they're given is it's UTAG based, and that's it.
I think some extra stuff needs to be done, because what if the data was already there at one of the private cache, and then but it's not found there, and the access goes further to DRAM, let's say.
Yeah,
So
the coherence domain should be aware of it, right? Otherwise, it will lead
yes.
to
Yes. Mhm. Yes.
Okay. Mhm.
Hello, Shimon here. So actually, I joined 2 minutes late, so I might have missed something. But my question is like, how does the attacker like find out the particular conflict set? Do the authors mention that? Or?
Like
Yeah, you
the
just
reverse engineered,
take all the virtual address.
like you first,
Okay,
okay,
sure.
conflict set
Yeah.
in which context? The reverse engineering part or conflicting mutags?
No, the attacker needs to know like which physical address. I mean, it wants to attack, right? Or
No,
Not
they need to know
physical,
only the
right?
virtual address,
Yeah.
what they want to attack. Since
It's
the
L1 cache.
yeah.
okay, okay, yeah. Then I might have missed something at the first. Yeah. Okay.
Yeah, hello. I have a doubt in this thread-based attack. Can you explain it in more detail? Like, what's the use of it? And
The load plus reload or collide plus probe?
yeah, in Collide plus Probe, if I remember.
Yeah. So like, did you get the part about the way predictor?
Yes.
Yeah. So like when suppose the attacker loads his address in, like step 2 is done, he accesses V prime, which has the same utag H. So here, the way predictor state is going to mark the way that he has loaded it into, with the muta corresponding for it.
Yes.
And then when if the victim does not access, then it's going to get returned from L1. Since there's a mutag match, it checks a physical tag at way 2 that also matches and it's returned. On the other hand, if the victim had accessed the virtual address V, it will be loaded into a different way, but the mutag will be same. So as I mentioned before, similar to how in the same set, two physical tags cannot exist at the same time and both be valid, both of them being the same. Similarly, in the way predictor, two different ways with the same mutag and both of them being valid is not permitted. So once this was loaded and the mutag entry here was marked as H, way 2's mutag value will be marked invalid.
Okay.
So when I access it again, since this was invalid, the only match was way 3, which it will load and then it will check the physical tag, which will mismatch, since these both are mapping to the two different physical addresses. And the mismatch will mean that it will have to go to L2 to fetch the data again.
Okay, yeah, got it.
Okay, then we can move on to the next presentation.
Hello. Hello, sir. Sir, can I present my screen?
Yes. It would be good if you can switch on your camera too.
Sure, sir. Sure, sir. Sir, is my screen visual?
Yes. The slides look scary. Let's see.
Hello. So we are team. So leave for 10 seconds. My name is Ajay, and we are presenting on the topic for testing timers and where to find them. High resolution micro architectural attacks in JavaScript. So basically, to just give you an outline, presentation is divided highly into 4 parts. Firstly, we will introduce like what is like we are talking about like just a problem. What is a problem? And then we come with a solution like using high resolution timers which are built in JavaScript. Then using this high resolution timer, we will do a DRAM attack. And after that, we will suggest some countermeasures. And then we will come to conclusion. So before coming to introduction part, I was on to ask like, is your browser safe? So you might think like your browser is secure from like all kinds of like your all secrets in the browser are preserved, but like it might be possible like someone is watching your secrets from behind. So let's find out. So basically, this is like interesting combo between like spy and the browser vendors. So like spy can say like warn the vendors like they can read browser secrets, but like browser vendor responded in a like a surprising way. Then they do some row hammer and cover channel attacks using JavaScript on the browser using this performance.now, which is like a function of the JavaScript which has initially nanoseconds of time resolution. Then as a quick fix to prevent these attacks, what browser did, they have lowered the resolution of performance.now function from nanosecond to millisecond so that these attacks won't be possible. But then like what suggested in paper, like it's still like browser not safe. Still like using some other channels, these high resolution timers can be built in JavaScript and which can be used to do attacks. So this is what like so the paper basically they are trying to build some high resolution timers which can be used to get the time in nanoseconds for the attacks. So this is like this is mainly to highlight like before this like suppose like before this version of Firefox, you can see like the timing resolution is 1 nanoseconds, but after the attack they have mitigated this performance.now function resolution to 5 microseconds, so that these attacks won't be possible. Even like Tor browser has penalized it to like into millisecond, so to prevent these attacks in the browser. So this slide is to just to give like why we need high resolution timers, because for a DRAM attack, if we see like between the row hits and row conflicts, the timing difference needed is very low. That is like 22 cycles. That is in a nanosecond. So that's why we need high resolution timer. So now coming to second part, like why like some high resolution timers which are built using JavaScript. So first one is clock interpolation. So what clock interpolation is basically, suppose like you have a clock, and like so what it did, like it increments a variable between the clock edges. So basically it start measuring a counter at the start of the clock and increment a variable until the next clock edge. And so and we did this step suppose like in 10 times the loops to get an average number of increments in a one clock cycle. Using that we get like what is the timing of one increment operation. So using this like we get accuracy up to 500 nanosecond. Now we will see through animation like how we'll use it. Suppose this is like your starting edge of the clock basically, and this is your functions, and you run like you were able to run 7 increment operation within like one clock cycle along with this function. Suppose in the previous step you calculated like one increment operation takes x unit of time, and like between two clock edges there is a y units of time, then you can easily conclude like your function take y minus 7x units of time. So that is how like clock interpolation method is used to calculate the timing which is like low resolution than this which this clock provide. This is like some code which is like written to calculate this time. Basically most like these three are the helper functions. So I will tell you like a little about each of them. Like what is weightage? Weightage is just aligning the cycle to the start of the clock. Basically it is waiting to clock to start so that we can start our counting at the when the clock has just started. Then this is calibrate is basically it is counting like how many what is the time taken by one count operation. It is like averaging over the 10 measurements and like calculating like what is a time taken by one count operation to increment counter from 1 to 2 just. And this is like incrementing the count until the next clock cycle is reached. So using these three functions we are basically like able to calculate the timing of this function 17 function in using this measure function call. So yeah, so in a previous method we are calculating the absolute time, but in these attacks we don't need the absolute time, we just need a relative time, like which we just need to find out like which functions run faster. So that's intuition between S thresholding. You don't need like absolute time, you just need a basically a relative time, like which function is faster and which is slower. So what this function is about, basically you have suppose two functions which you want to distinguish, but now you won't be able to distinguish them because they lies between a one clock cycle. So your time resolution is won't enough so that you can distinguish like which is slower and which is faster. So what you did, you add padding. What is padding? Padding is a like multiple constant time operation. It may be as simple as incrementing a count. So you add padding to both the function f slow and f fast, and you adding padding in such a way like your slow function just crosses one more clock cycle age as compared to your fast function. So now if you run like this function along with this padding, you are able to deduce like this because now they lie on a different resolution clock. So you are able to deduce like which one is faster and which one is slower. And using this you are able to find out basically whether like which function run slower and which function run faster. So using this you can even like do it as a timer for attack. Third one is message passing. So what message passing is, basically you have a main thread Yeah, so main thread spawn a subworker thread. Also, what subworker thread do? It spawn it has spawn another thread which is subworker 2. So this subworker and subworker 2 combinedly act as a timer. Basically, subworker keep on sending message to the subworker 2, and on each message received, it increment the count and send the current counter value to the subworker. So it keep on going like this in the background. And whenever the main thread needs a time, it requests a time from subworker, and subworker returns it the current timer value. So basically, using this, like this process keeps on going in background, and like whenever main thread wants a time, it can request a time. So basically, it's like a logical clock which is running. So yeah, so using this even like you can deduce like the difference timing of the two functions. Another one they have mentioned is like a shared array buffer. So what like shared array buffer is like common shared memory in a JavaScript which is shared between the two threads. So how we are using it it is just like a stopwatch. Basically, you run a separate thread which is just whose function is just to increment the counter in a shared memory buffer in a memory at a shared memory buffer. So this counting thread is just incrementing the counter at the back in this shared array buffer. And whenever like this main worker wants to read the value, it can directly read from shared array buffer. So basically, this is like just like a stopwatch. Basically, one worker is running like a stopwatch in this shared array buffer, and when the main thread wants to read it, it can read it. So this is another method to build this timer. Even like this method is the best one, and even they have revived the cache attacks. Like this is just to like basically like after the increase of the resolution, cache attacks won't be able to possible in the browser. But using this shared array buffer technique, the author has done this cache attack even in the using the browser, using the JavaScript. And this is like another method which is like CSS animation. Basically, suppose like you have some width of the element, so it width increases within some time. Suppose you have built some element in
Hey,
CSS.
hang on. What is width? What is element?
Okay, sorry. Yeah. So basically, suppose you have some image. Basically, who have some pixels. Pixels basically uh, 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 basically
Cool down, cool down, cool down. It's okay.
width is basically a resolution of pixel. Suppose a pixel, suppose when an element load, it loads in the form of frames like pixels. So suppose you have some element which whose range width is like from 0 to 1000 pixels. So basically it and you have animated in such a way like it takes 1 second to load the whole picture. Okay, but so by retrieving the current width of the element, like at particular timestamp, you can find out like what is the timing. But this is not a good method because like like most of the animations are limited to 60 frames per second. So which limits this timer's timing up to 60 milliseconds basically. So which is not a good resolution to get for this. Now like basically this table is like they have evaluated like all these all these high resolution counters on a different browsers, and they find out like last three like shared array buffer, this interpolation and the thresholding have their resolution in the nanosecond which is required. And this like just to mention like this fuzzy box, what is fuzzy box? Basically on fuzzy box what it did like it randomized the time basically. So basically what is randomized of time means like it add jitters in the clock. So by adding jitter in the clock, interpolation and thresholding is not able to work. But yeah, even like a shared array buffer works here too. So the shared array buffer comes out the best solution till now for building this high resolution timer, because it has very low resolution time, 2 nanoseconds, and even it works like with a one mitigation, like which is like randomized the clock. So that is like takeaway from this slide. Now like coming to like DRAM attacks using these timers. So basically let's just like a brush up like what is covered channel. Basically in covered channels, like two programs like to communicate, but they are not allowed to communicate, so they use side channels to communication. Now like some other like basically our DRAM is organized in the form of channels, and there are racks and chips. If I go inside one big chip, then there are various banks, and within one bank there are various rows and a row buffer. So yeah, like this is made of capacitor and cell, like one capacitor and one transistor each. Now, how you read data from DRAM? For this is a picture of one bank, and whenever you want to read, firstly you activate that row, you load into the row buffer, and that row buffer is written to the CPU. So this is the way in which like DRAM is accessed. And like if you now if you want to access now same row again, like the row will be directly fetched from the row buffer instead of here. So that's some timing difference we are getting using this DRAM by reading from DRAM. So yeah, using this, like they have done the DRAM covered channel attack. Basically, as a pre-step, like sender and receiver has to agree on a bank, like which bank they have to. This to be hard coded. Like they have to agree on this before. Now, the sender is basically sender is running inside a VM virtual machine, and this receiver is running as a JavaScript, and both have decided on a different row inside the same bank. And we use JavaScript shared buffer timer to access the timing for each row. If sender want to transmit 0, it will do nothing, and it will transmit 1 by causing a wrong conflict. We will see like this through animation how it is doing. So basically, like if access was fast, the sender want to transmit 0, otherwise sender want to transmit 1. So basically, this is like this is a one bank, and like sender has chosen like row 1 and row 0 and row 1, and receiver has chosen row 2 and row 3. Now basically, what receiver do, it access it row and copy it in, like and measure it access time. Initially, the first access have high time because it should be come from a row and loaded into row buffer, so its access time should be high. Now repeated access time has low access time because it is directly fetched from the row buffer. Now, if sender has to send a 0, it will do nothing. Receiver will just repeatedly access it rows from the row buffer, and it will get a hit, and like it will get a low access time. So it will know, like it will can infer like the sender can want to send 0. On the other hand, when it want to send 1, sender accesses address and load into a row buffer. Now the row of the receiver is no longer in the row buffer. So basically, when receiver want to access its row, it is a row miss, and so access time is again high. So receiver can infer like sender want to send 1 through this. Yeah. So this is how like they are like they are communicating. So now some of the countermeasures. These are countermeasures to like stop like which helps to prevent the resolution of those timers we have just discussed. So first step is like to prevent like these first two methods, clock interpolation and as thresholding. So basically what we did, we randomized the H clock. We basically adding random jitters to the clock, which through which we do not able to do interpolation step. Because as clock is randomized, it's not able to possible. Second one is like this is for shared array buffer, in which like you are parallelizing and running a different thread which is acting as a counter. So if you make a thread affinity of same CPU code, then that parallelism is not possible. Basically, then these have to, there is a context switch, but like sometimes that counter run, sometimes that main thread run. So the resolution will be not that high as compared to when there is a parallelism. And third is like increasing the latency in massive passing. This is to like for massive passing method, like in which like there is we have discussed like sub worker and sub worker 2. So if you increasing the latency, then again like the resolution will be lowered. It will not that resolute, because if you increase the timing of the massive passing, then like the resolution of the timer will decrease. So these are some of the countermeasures. And finally, coming to conclusion, like just rounding timers, like increasing like the lowering the resolution of performance down is not a solution. And like multi-threading is very useful technique, which is like we can see like shared array buffer and message passing both are built on multi-threading techniques. So they are important. It is very important to build. It is very important technique which is used to build new timers. And shared data always come with great risk, because we know like shared array buffer, which proves to be a best method, has exploited the shared memory concept. And it is built it is now possible to build again nanosecond resolution timers in JavaScript, and microarchitectural attacks in the browsers are possible again. Thank you. Any questions?
No questions, is it?
Yeah, hi, this is Arnav. Can you go to the evaluation slide? Just one.
Yeah. Evaluating.
Evaluation slide number 19.
Yeah.
Here we can see the set timeout is also a good option, right? If you remove the fuzzy box option and other Firefox and Chrome and Edge, everyone it is working, right? So why not use it and instead of shared buffer array?
Set timeout. You're saying set timeout.
Yeah. Second option.
It's giving it in milliseconds, right?
It's
rather than in nanoseconds.
Oh, sorry. My mistake. Sorry.
But is the takeaway clear? That this paper has pretty interesting ideas, set of ideas. Okay, I don't have many queries or questions. Just a comment. Maybe you should not have jumped into the DRAM part. That was a bit of digression.
Okay, sir.
Maybe you should have spent more on this. The DRAM covert channel is kind of straightforward, as we have already discussed.
Yes, sir.
But the key here was the timers part, right? Once you know how to create a timer at a pretty precise nanosecond level, then yeah, you can do any attack that needs precise differentiator, right?
Right.
Yeah, and then have slide numbers in slides. That makes it easy for others to point out.
Yes, sir. We forget that actually. We will keep.
I think you're using a different template. I think that's why. Otherwise, I think Devasys shared a template where slide numbers were there. It was subsumed, I guess.
Okay, sir. Sorry, sir. I will look in. I will for next time. I will keep that in mind.
Okay. Hey, any other questions?
Yes, so in case of edge thresholding, how you figure out that the particular threshold or the particular clock has been reached out? I mean, in case when you're operating, like
so basically, we have to add this padding, right? Like so basically this is a pre-step. Like you have to select that padding first. Like for the test rounding method, like you have to select that padding. So you have to tune it basically. So what you did, like
but how?
Yeah. So suppose like you you pick a function, then you keep on adding a like these operations, right? This like suppose this padding is like increment operation, right? So you keep adding to that function, okay? And at the same time, you will keep on measuring your clock using performance.now. As soon as like your clock will show a different time from a previous one, like, because like here what it did, it shows the same time between these two disk cycle, right? As soon as it crosses this edge, it will cross different time. So you will select the padding in that way.
So this is an iterative process. You kind of add a few statements or counters or whatever in your code, and then check the timer again, right?
Yes,
then suddenly you realize, okay, now the timer is throwing a different value.
Yes, sir.
That's where you decide, okay, this should be my padding, right?
Yes, sir. Exactly.
Yeah, I was there having this idea like when you're applying low pay, basically it's like, I mean, okay, some microseconds, but for nanosecond level, I mean, which kind of extra code you can put in the code? That's what I was thinking. Because if you
put some junk which will just take time. That's all. Right.
They've just done count plus in this case.
Yeah, that's what it's okay, right? Yeah. But count plus alone won't be helpful, right?
So like you can do multiple count operations, right? Like not.
Yeah, that's what.
Yeah.
Yeah, it depends on the edge, how far or how near you are from the edge, right?
Yes.
Based on that.
Yes.
Yeah, this is pretty interesting work. I have read it a long time back, and I still like this paper. This idea is awesome, actually.
I have one question regarding this padding only. Tejeshwar here. So what about out of order execution? The noise created because of that, because you wrote the program in that order, but that doesn't guarantee that it will be executed in that order, no? And
Basically,
since you are dealing with timings which are pretty close to the clock cycles, so the sequence in which they are actually executed will matter, will affect your padding, right?
Basically, you are saying like, suppose somebody is running this function, and you get like noise, like another program run in between,
No,
right?
you have two executions. One execution is a slow function plus padding, and another execution is your fast function plus padding.
Right, right.
Okay. Now, in these two executions, both of them will be executed in out of order. So you cannot guaranteedly say that your padding will be executed later on, or padding will be executed in that order only. It might find some blank slots between your slow function and fill them with your padding. And it may happen that your padding and slow function, both of them are finishing like ultimately on the same cycle. They'll retire one after another, but the execution might happen when there are stalls in the slow function. So this will affect the accuracy, right?
I don't think it will matter, because I mean it's we already know how much padding we are adding, so whether it
No, no,
executed before.
Mahindra, what Tejaswar is suggesting is you know that you have to add this padding instructions at the end. Let's say at the let's say just at the end of the function before it ends, you add this, right? But because of out of order processing, the processor can decide to execute those instructions in the beginning itself, or maybe somewhere else, right?
Yeah, but sir, we are just here. We are adding padding just to increase the overall duration of the function, right?
Yeah, we are
Yeah, so
increasing
duration
it
will
any
change.
moment won't much affect that, but
Yeah,
because
yeah.
overall you want to increase the duration,
So
that
if
you
you
can see the
run
difference.
if you run the slow function alone, since it is slow, I'm assuming there might be some stalls, there might be some memory accesses or something for which the execution unit is waiting. It is not doing anything. So padding will just fill up those slots. So ultimately your execution time won't be affected by that much. But in case of fast, I'm assuming there aren't any, like not that many memory accesses or not that many stalls. In that case, padding will take extra cycles.
In that case, might have to choose functions which are basically total CPU dependent only, and then we can increase the padding so that IO
These are
outs
not
won't get
novel method.
overheaded.
No, but the other way is to just go for fence, right? If I put a fence, and then make sure
something
that
like that need to be done.
then it's okay. I think that's what people do whenever they talk about timing, they put a fence before and after. If you look at the source code of any attack, the moment that they write a function to extract the latency or time, you will find there will be fences.
No, but sir, how the IO? I mean, the IO operation will be separately done, right? The fence.
IO, no, we are not talking about IO here, right?
No, that's one of the things mentioned was like, what if there in the slow function there is some IO request, which is increasing
Okay,
the
then
time
it won't.
duration. Then it might affect, right? So basically, we have to
yeah.
choose the slow functions like they are completely CPU dependent only. Much less of IO is there, so that increasing the time is actually increasing the time, not just filling up the gaps.
Yeah, because this fence instructions, they won't affect IO.
Yes.
IO will continue through DMA.
But
okay, it's a good point. Okay, anything else, or we'll start the last one?
Hello, am I audible and is my screen visible?
Yeah, but I can't see you.
Okay, sorry. Just a second. So, am I visible now?
Yes. You are in a jungle, is it?
No, sir.
Okay, go on.
Okay, so I'm Sahil Jain from the team ArcMages, and today we'll be presenting this paper named Record Replay Architecture as a general security framework And what is this paper about? So first of all, let's talk about security features and hardware and what is their current status. So some of them are imprecise, probably because there are false positives or false negatives which they are not able to detect and uh, handle them properly. Then some of
Hey,
these.
sorry, I didn't get the context. What is false positive here when you talk about hardware security?
So by false positives, I mean like, for example, there is, so it will come up later, but an example is that like suppose you are doing an ROP attack. Suppose an attacker is doing an ROP attack who assesses if there is some uh, underflow or maybe there is some return instruction which did not have a call associated with it, for example. So those things.
So
No, no, no,
false
no.
positive means that
Uh,
you say that an attack is happening, but actually there's no attack.
that I know, yeah. I know the definition of false positive. Come on. I just want to connect with the title itself. You started with hardware security and then you said there are some false positive. I just wanted to know like where exactly you are going.
So basically, we are talking about how hardwares implement security features and what is not so good about them.
Okay,
And
so these features are imprecise, and then that's why you are saying because they are false positive and blah blah blah, right? Is that
yeah,
correct?
yeah.
Okay, okay, okay.
And maybe some of these features, some of these security features that are required are intrusive. So they have to do extremely complicated changes in the hardware to ensure that the hardware
Okay.
becomes secure.
Got it, got it, got it. Yeah, go
And
on.
they are inflexible. So for example, you might prevent one attack, but to prevent another attack, you might have to undo the features that you had originally put in. So these are the issues with security features in hardware. And of course, we have these security requirements that, well, false positives and negatives are usually not acceptable, especially false negatives, and less intrusive the hardware, less complicated it is and lesser the cost. Therefore, we want that the hardware be non-intrusive, and we want flexibility because attacks keep on evolving as time progresses, and so must our defense. So can we get security that is precise, cheap, and flexible? So that's where R&R safe, the topic of this paper, comes in. So first of all, we begin by talking about, let's talk about the outline of this presentation. So first of all, we'll talk about this R&R safe, a general framework. Then we will look at it in the context of an example threat, which is stack smashing and ROP. Then we will talk a little bit about prior work on ROP, prior work on defenses against ROP and their limitations. And then we will discuss ROP in context with R&R safe, some details, as well as finally experimental evaluation and results. So first of all, what is R&R? Record and deterministic replay. What this means is that you perform attack detection via replay of whatever program execution happened, and deterministic because we want to ensure that whatever events, for example, interrupts or network calls or IO, whatever happened, we want to replay them as it is. So there are two parts to this, recording and replaying. So recording, deterministic events are just fine. For example, any instruction was executed because the program counter was pointing there, that's deterministic, okay. Non-deterministic events, they are saved in a log so that they can be replayed easily. And well, just a second. How do we replay? Deterministic events can simply be reproduced via re-execution of the program, while non-deterministic events such as interrupts, network calls, whatever, IO, etc. I mean, all these things can be reproduced from the log because they were saved. So this is record and replay, and this framework has been used in many places, including, of course, attack detection, auditing of attacks happened on systems, etc. So what is R&R safe? R&R safe is a framework which is used to complement the hardware security features such that the whole framework plus the hardware now has all our requirements that we previously mentioned: precise, less intrusive, and flexible. And several checks are actually offloaded from the hardware to the framework so that the hardware changes in the hardware become easier. And RNR safe is organized as follows. So any workload that you want to execute is inside this recorded VM, runs inside this recorded VM, and then a hypervisor, that is the thing that runs outside the VM and which controls how the VM runs. So this hypervisor will log all the inputs as well as any alarms if raised by the hypervisor due to possible attacks and such. They are put in this log. And then this log is then replayed at two replayers. One is called a checkpointing replayer, another is called an alarm replayer. And we will discuss these checkpoints and checkpointing replayer and alarm replayer in more detail. But essentially, this checkpointing replayer or CR will memorize the states as checkpoints from which this AR alarm replayer will later fire off and perform detailed investigation of these possible alarms raised. Note that all the diagrams and graphs in this paper, in this presentation, are taken from this paper unless mentioned otherwise.
Hey,
So,
Sahil, I have a doubt here.
Yeah.
So the goal of this framework is to provide an information that whether you are under attack, is it?
Yes.
But that will happen after the attack is over, right?
Actually, you can perform that while the attack is running as well. Right. I mean, suppose one step of the attack is, suppose the attacker is attacking in steps, then you can check on each step. Like if the step one looked like a primitive to an attack, you can stop the attack from happening there itself.
Okay, so maybe just a confusion. So in the previous slides, you said that you will replay the entire program in execution, right? And then the deterministic paths are kind of anyway that they are deterministic.
So it is being replayed while recording takes place.
Okay.
Recording is continuous as well as replaying is continuous, and the CR is actually the main replayer which keeps on working all the while this AR is fired only when there are alarms in the log.
Got it. So it's like these are like two threads which are running concurrently along with your, let's say, benign and attackers, and they are kind of monitoring it, right?
Except CR always runs, yes. AR
yeah.
can be multiple threads. They can be several of them fired together.
And the practical utility is hypervisor has to do all these things.
So hypervisor has to record. Yeah.
Okay.
And of course, there will be some changes required in the hypervisor, etc.
Obviously.
And the hardware as well. So those things are, of course, going to be there.
Okay.
Yeah. Shall I proceed?
Yeah, sure. I'm clear. Yeah.
Okay. There is one additional thing here. So false negatives, as we mentioned, are not at all allowed. So if you're unable to detect an attack, that has a much higher cost than detecting a benign execution as an attack. So in this framework, what is going to happen is that hypervisor is going to use some, so it was going to be mentioned there, like there is some alarm trigger, which is definitely going to be triggered when there is an attack. And then what this means is that there are no false negatives, because in case of an attack, the trigger is always triggered, but there can be false positives, which might have to be detected and then figured out that these are false positives. So we have possible first detection techniques and what the replayer has to do. These are possible applications of RNR safe to various attacks such as return-oriented programming, ROP, jump-oriented programming, JOP, and denial of service, DOS. We will, in this presentation, be looking at ROP only, and ROP follows next. So,
Okay. Hang on. Now, can you go back to previous slide?
We will.
Yes.
These things,
yeah. That's okay. I'm not asking anything now. I'm just curious about this DOS attack. So in the denial of service, you are saying the alarm trigger is kernel scheduler is inactive.
Yeah, so actually they are looking at the kernel DOS attacks. And apparently, like, yeah, I think it was like when the kernel is not scheduling any activities for a while because possibly the kernel has been DOSed and is not like running properly or is running slowly. I think that.
Even if there are active processes that are running on a system. That's the scenario.
Yeah.
Okay.
Hello.
Yeah. Okay. Maybe you can move on.
Okay. Sure. So over here we will be talking about an example thread ROP, but in context of kernels. So first of all, some background on ROP and stack smashing. What's stack smashing? So suppose we consider this function which has an array of length 32, and then you're copying something into this array from an input. However, there are no checks whether what you are copying is indeed 32-bit long, sorry, 30 has length 32 or not. It could possibly have more. It could possibly be like 100 bytes, and what happens in those cases? Hello, am I still audible? I think.
Yeah, everything is okay.
Yeah,
At
audible.
least. Yeah.
Okay. So let's look at how the stack looks like when this array is like when this program is compiled and then executed, what the stack looks like, and then what could possibly happen in case of an overflow. So note that this array will be allocated on the stack because it's because it's a local array inside the function. And then we would have this return instruction, return address, actually, not the instruction, but return address below this array after some, let's say, after some bytes. And what might happen is that suppose you are providing an input which is, no, let's think for a while. Like suppose it's 100 bytes long. Suppose that's what the input looks like. Then you are
Hey,
essentially
make
copying.
it simple. You are complicating it.
Yeah.
Yeah. Just maybe pause for a second and then make it simple. Yeah.
Okay. Yeah. So suppose you have 100 bytes. Right. Suppose now we are copying those 100 bytes into this array. This is only 32 bytes long. So where do those 100 bytes go? They are going to override whatever lies below this array in the stack. So we have a return address recorded of the function from which this func was called. So that might also get overwritten. And that's the crux of the stack smashing attack, essentially, that you put in some malicious code over here and you modify this return address because there is an overflow. You are able to modify this return address such that you can execute your own code. So essentially, when such an input is given, attack code and some address, that attack code is put over here, and then this address is overwriting this red from red to black. And now this red points to this attack code, and therefore this code gets executed. So essentially, you're injecting your malware by attacking the stack. However, so this is an attack quite famous, and it's been more than 20 years since this attack is known. However, there is a technique to prevent this kind of attacks, which is called WXRX. What this means is, note that stack is always writable. You can whenever the program is running, whatever data lives on the stack is always writable, can be modified. So this means WXRX means that whatever pages are writable, you make sure that they are not executable and vice versa. So for example, stack over here is made not executable. What this means is that even if you push this attack code over here, you won't be able to jump to it because it's no more executable. So essentially, whatever malware you injected can no longer be executed. So can you not attack it anymore? Actually, you can. So note that stack is not executable. Therefore, you cannot write any code into the program that's running. But of course, you can always reuse the existing code. So this just prevents code, what do you call it? Code writes, but it does not prevent code reuse. So let's think about it for a while. Suppose that the attacker, like, suppose that the attacker wants to execute something like instruction 1 with some data, instruction 2 with some data, instruction 3 with some data. Now he tries to find these instructions inside the binary itself. Okay. So the binary or the program is always there. He tries to find the address of this instruction with the return next to it. Similarly, instruction 2 with the return next to it, instruction 3 with the return next to it. These are called gadgets. And suppose that the PC is at instruction 1. That is, the PC is equal to address 1. If not, there are possibilities on how to do it. Like you can simply reuse the ret you had, but it's not necessary to describe what we are going to do next. So now suppose that you're providing an input such as data 1 something something something. This lies on the stack. Okay. Now this instruction 1 fetches data from the stack, which is data 1. Okay. Return. What does this return do? This will pick up this address 2. And this address 2 was precisely this instruction 2. What this means is that after executing this ret, you will jump over to this address 2. Similarly, you will take the data for instruction 2. Then you have another ret, which means that this address 3 will be where you're jumping off to next. And so you now have instruction 3 taking its data 3 and then return. What this means is that you executed some code of your own, actually, but which was already there in the binary itself. Of course, you are not allowed to put in any extra code, but you executed it, which is an abnormal flow. So normally this would not have happened had there not been an overflow, and had you not been able to modify that ret, whatever return address to this ADR1, for example, or ADR2 maybe. So of course, it has been shown that this return-oriented programming, also known as ROP, is actually Turing complete, given enough gadgets and what that
Sahil,
means. Yeah.
I have a doubt here. So, so this input will again be the input to array, right?
Yeah. This input. There was a char star input, right?
Yeah.
This
Yeah, exactly. Yes. So it's just that before the return, you are writing whatever you just mentioned, instruction, then return, and like that, right?
You can do that, or actually, since you modified this ret over here to point to this, you could modify it to point to ADR1.
Yeah, but like the, I mean, in the next slide, the kind of input you showed there, you are not overwriting the return, right? The ret you are not overwriting there, or are you?
Actually, yeah, it builds from that. Yeah, but it is supposed to do that, yes.
No, my question is that so the return address of that function is not actually overwritten. Whatever you have, the kind of input that you are providing to the array.
So that, yeah, what you want to do is you want to modify the flow of the program.
Yeah.
Possible ways you can do it is, I mean, in these slides, the possible ways that you can do it is by modifying this return address in of the function.
Yeah. Yes. Yeah.
So this return address will have to be modified. So here we put it to this attack code. However, in the ROP, we will have to put this return to the first gadget. So consider a sequence of gadgets. You have to put it to the first gadget. And from there, you go to the next gadget. And that is how you build a chain. So what this means is that had there been not an overflow, you would not have been able to write this ret.
Okay. Okay, yeah. Thanks.
It kind of builds from that slide, actually, yeah. But that's how. So this basically you are able to make a chain of of whatever gadgets you wanted, and this is shown to be Turing complete. That is, you can do almost anything with this. You can build a program inside the running program consisting just of ROP gadgets. So how do we fix this now? WXRX does not work anymore. So how do we fix this? There are a few techniques. However, all of them are either they have one of the mentioned mitigations. So for example, these ones have intrusive hardware changes, as well as they use some privileged instructions which are actually exploitable. There's this another instrumentation based control flow integrity enforcing solutions. These have overheads of over 100% when modifying the binary, the program. So you have to essentially replicate the program by modifying the call and write instructions, and that adds a lot of overhead. Then there is this ASLR address, uh, I think address space location randomization, something of that sort.
Layout
Oh,
randomization.
layout,
Yeah.
address space layout randomization. What this means is that the code, data, etc., all these various segments, etc., are randomized across the whole address space. However, there are address disclosure vulnerabilities which can be used to bypass this ASLR as well. And then there are also blind ROP attacks that have been done. Essentially, all of these are limited in one or the other manner. Either you cannot prevent the attacks, or you have to have quite high overheads. So that's where RNR safe comes in against ROP. Note that so let's first talk about something called return address stack. So what's RAS, or return address stack? It's a hardware structure used to predict return targets. So for example, let's consider this scenario when the species is at call func, and therefore RAS contains the address of this next instruction. Then you move inside func, you call func to, so here you are, like this ret is also going to be put here. And on the stack also, of course, you're going to push the return addresses because that's how function calls happen. So you have the first return address, you have the second return address. Then inside func2, you execute something, then you ret. And of course, so note that stack is where you take the return address from, while RAS is just used to predict these return targets. So note that these two are matching. That is where you will return to would be this red ret. So you're good. Similarly, you return to this red. Again, these two are matching. You are again good. You return here. No mispredictions in whatever you did. Think of the same RAS in case of an ROP. To go to call func again, there is some vulnerability inside this function which allows an attacker to put something over here. And so he put in this gadget something, gadget something. Okay. Basically gadget address actually. Yeah, because, and here is the gadget. So this is the gadget address. You return to this guy. Stack will contain this because that's what the attacker did. Okay, earlier it contained this return address, but that's now been modified, while RAS still contains this old return prediction. And now you can clearly observe that these two are not matching, basically a misprediction. What I'm trying to mention over here is that a simple way to prevent ROP would have been to ensure that you're returning to where you began from. However, there are reasons to why this cannot be done, including overheads and possibly integrity and other things. However, like those limitations would not show up over here because we will do something additional. That's what comes up next. So RAS is not the full solution to ROP in itself, but we are just using this RAS misprediction to do what we want to do. And of course, the attack continues, whatever. So RAS misprediction can be used as a detector for ROP. Any ROP attack has to make at least one misprediction. That is, there are no false negatives. However, there can be mispredictions other than ROP. Therefore, we have possible false positives. What these can be of, these can be of 4 kinds in kernel ROP, because that's what we are looking at. So multi-threading returns when no call was done. Underflow, that is RAS is a hardware structure. Its size would be limited. You might do more function
Hey,
calls
this
in
is
this
this
sense.
necessary to talk about all these things? I think we should connect back to R&R, right?
Yeah, that's just coming up.
Hmm.
Actually, so all of this is going to be in context of R&R safe on what follows. Because they're one of the keywords is also reducing false positives. So like they propose some hardware changes as such to prevent, like for example, what they are doing is they are maintaining a per thread RAS in the hypervisor and not accessible by the kernel, because their threat model kind of assumes that kernel codes could have any kinds of vulnerabilities, including address disclosure, that is reads, or possible overflows that we just showed earlier. And this RAS is then updated on context switches between these threads. So this is how they fix this multi-threading mispredictions. And how this works is like you have a guest that is running thread I. Now you want to do a context switch from I to J. You do some hardware transition, hypervisor does something, and these back RAS things are updated properly, and thread J runs. Okay, these are further details. So what are non-procedural returns? You have something like an address is pushed to the stack, and then you return to that address without doing any call. And this is actually present in the kernel when Linux scheduler, for example, kicks in, but this was observed at only one place inside the Linux kernel by the authors, and only a few possible return addresses. So what they propose is that we will store these return to target mappings, and we will whitelist these mappings so that these do not perform RAS mispredictions as such. Okay. And then, so these are all changes done in the hypervisor and the hardware. None of these concerned with replays just yet, but what follows next is underflows. So that's because hardware data structure is of course going to be limited in size. And you might in those scenarios evict older return addresses, resulting in mispredictions. These things are difficult to tackle in hardware. So this is what is going to happen inside the alarm replayer and checkpoint replayer, for example, that you're to prevent to avoid complicated changes in the hardware, you do something detailed analysis in the softwares. Okay, so these are details on how that is done, and then there could be exception handling, which could result in calls without return. For example, maybe you have a sequence of exceptions from inside functions. These are rare, but again require extremely complicated hardware, therefore handled inside software. Now we detail on checkpointing replayer. Essentially, you store the input log pointer, back arrays, and memory pages, processor state, and disk blocks. And as time progresses, the next checkpoint could have same pages from the previous checkpoint, which you could just refer to. And if there have been any changes, those are the updated pages. So all the VM state is there, back RAS array storing RAS per thread is there, and then pointers to the input log as to tell where you have processed is there. Okay, this is checkpointing replayer, essentially used to just perform checkpoints. And
Hi,
then
Sahil, I have a question, if you don't mind. Yeah, actually, what is the interval of these checkpoints? I mean, in what particular interval these checkpoints are been taking place? It's like a constant interval, or it's varying with time?
Yeah, in experiments, they are actually doing it per a few seconds, and they experiment with different values of those constant time intervals. Okay.
So it is not like for an actual, it's not like fixed particular value, right? It depends on the implementation kind of you want to have on the system.
Yeah. So the authors haven't specified what this could be, for example, or what it has to be. Nothing of that sort.
Thanks.
Okay. So what does alarm replayer do? So in the input log, you might find alarms, for example. There are inputs over there, but of course there could be alarms because possibly RAS misprediction occurred, which was recorded in the log. So when the CR finds an alarm, it launches this alarm replayer, and it could launch from any of the checkpoints, and it could load all the saved state and execute the whole workload, however, performing detailed analysis. For example, now earlier you just managed to do things with the limited hardware RAS, but now you have to do simulate unbounded RAS inside software. So yeah, that's how you detect whether a false positive is actually a false alarm, whether an alarm is actually a false positive or a real ROP attack. So okay, and then there were so this is all about implementing all of these things inside R&R safe. Some of these offload to hypervisor, some of these offload to CR, some of these offload to AR. Now onto experimental evaluation. So the authors use two kind of setups. The recording and replaying is actually done using an inside VM.
Hey, Sahil, how much more time you need?
2-3 minutes.
Okay. Your slides are actually too dense and you are reading. That's kind of boring. So yeah, move on.
Yeah, okay. So for the hardware changes, they use KMO emulation. And so these are some results on, these are some experiments on how much overhead recording takes in and what are the possible, what are the different kinds of different reasons of overheads. So what is observed is that a recording, of course, has a substantial 27% overhead. However, it's and it's mostly dominated by RDTSC timers. Recording them takes most of the time, and saving and restoring RAS inside the hypervisor does not take a lot of time. What about false alarms? So how many false alarms are there? Actually, if you look at this, then there are some white lists which have been handled. Some other things have been handled by this back RAS. Well, false alarms are almost negligible, only a few for this Apache benchmark, which is mentioned at the top. And these few false alarms would then be passed on to the AR. So now on to some CR results. So how much overhead, how much time does replaying take with respect to recording? So it's not orders of magnitude different. It's like maybe 1.5 or twice than recording, but you can run them in parallel at comparable speeds, and you don't have to switch off replay if you ever want to do that. So that's not required over here. And then these are results on what could be different kinds of time intervals to checkpoint against. And again, some overhead distribution. Important thing is some asynchronous interrupts actually take a lot of time to replay. Now, what about alarm replayers, which does everything unbounded inside software? So it has a lot of slowdown and overhead as compared to normal recording. So if you were to observe this, for some benchmarks, it's even 50 times what recording or replaying was like. Well, for others, it's maybe in 30s or 20s on an average. So alarm replay is quite slow. However, since there are only a very few false alarms, this alarm replay, the slowdown does not affect our overall execution that much. So as
Yeah,
conclusion,
please
what is
don't read it. Don't read it.
sure.
It's
So
too, yeah.
what do we conclude from RNR safe? Hardware.
I'm saying don't read it.
Yeah, yeah.
It's
Sure.
okay. It's done. Okay.
Okay. Okay.
Yeah. So I don't know why this trend continues. You know, 3 paragraphs in a slide. It's kind of boring for audience like me. You know, extremely dense slides. Yeah, and most of the or all the figures and plots related to papers were from the paper itself. Copy paste.
That
Yeah.
was mentioned over one of these.
Yeah, I am okay with that. Instead, I would have, I'd have
No, so
appreciated if you'd have spent some
these
more time.
diagrams were ours.
Yeah,
These-
that I agree. Yeah, this I agree. But too much information, right? Yeah. Again, like so much hard work, but finally utility is pretty poor. At least in my humble opinion.
Okay. Sure,
Yeah,
sir.
so maybe for other groups who are planning to present from next week, try to take these as examples. So this is not a good presentation. Okay. Yeah, at least for this course. For other courses, it's okay. I don't mind. Okay, we are already running out of time. Thanks to the last presentation.
Sorry, I think I unshared. So are there any questions?
Yeah, I don't have any, but others can ask.
So Sahil, I had a question. Like you mentioned that write and executable permissions are not there in the victim machines stacks, right? But it seems that
You
victim
do write
machines,
XOR X.
right?
Yeah.
W and X bit you have shown, right? So now these victim machine stacks are visible to the attacker or third party because they are able to manipulate all
No.
these.
So the workload of whatever process is running inside the VM.
Okay.
So you are of course going to attack that process, maybe via network calls. Maybe it's accessible over some network or server. So you're not you do not have access to hypervisor, for example.
Okay, so the victim that's program stack you don't have accessible, but you are somehow you are changing the return address there, right?
Because yeah, you are providing it, right? You're providing the program some input, possibly like it takes in some form data, and that form data might contain the addresses and other things you want.
Okay.
So, okay, are there any other questions?
I was thinking, what if RASs are, being corrupted by the attacker? Because that's the sole point of this RNRs, right? Because you are changing the return addresses.
So note that first of all, RAS is a hardware thing. Okay.
No, you told like when you are expanding, it's like a software plus hardware, like virtualization you're doing for it.
So
and more of the process running.
So yeah, note that hypervisor. So what these authors did was this RAS was actually stored inside hypervisor. So this back RAS array was stored inside hypervisor, and RAS is a hardware thing, supposed to be at least. And the attack model we have is that we are targeting the kernel. We want to perform an ROP inside the kernel. So of course we do not have access to this hardware directly, and neither this hypervisor because it's beyond the kernel.
Some instructions you are using it to access the right. If not kernel, then the user mode you are using it.
No. We are not using any instructions. It's manipulated on its own with call and ret. Simply.
So Arnab, this is completely about your function calls and returns. So
okay.
Yeah, so there is no instruction which can go and manipulate these structures.
Yeah. And even if you try to do that, that's what we just showed, right? If you were to do ret without call, you're in trouble. So are there any other questions?
Okay, Devasius, stop the recording. And next week we don't have any presentations because that's the exam.